He's going to talk about owls, and I believe he'll try to justify why we have a logo like this.
Well, thank you very much, Anastasia, for the introduction and for organizing, you and the organizers for organizing the conference and the invitation to present. I'm talking about turbulence noise reductions by owls, which seem like odd bedfellows, Wiener-Hopf and owls. But as I was in Professor Speck's lecture on Monday, they've been trying to tell us to use the Wiener-Hopf operator all along. We've just been spelling it incorrectly the whole time. So I've been working on why owls are silent. I put silent in quotations because, of course, they make noise as they fly. But what are they doing to make themselves quieter in a region, a frequency range that's of importance to us and to them? For them to be effectively silent, they have to not, of course, alert their prey that they're coming. So you have to think about the sensitivity of their prey, and that's quite keen around 2 kilohertz and above into the ultrasound range for us. But the owls are quite sensitive in the 3 to 6 kilohertz range, and they do the targeting on the fly. So if you put them in a dark room, make noises on the floor, they'll correct on the fly for their prey. So for them, acoustic stealth means 2 to 6 kilohertz and above has to be suppressed to below threshold hearing levels. Okay, this has great implications for us. I'm an engineer by training. For applications, say, aviation and energy industries, because, well, it turns out we're quite keenly sensitive in that same frequency range. So we understand it at the owl scale, that'd be great, and can we transition what we learn about that to other technologies? And just to show you on a log scale where we hear, this is about 20 hertz out to about 20 kilohertz. I'm not sure I can hear quite that high anymore. That goes down with age. But peak hearing range is here, this dark gray. Here we have the peak hearing sensitivity for owls, and then the squeaks, rustles, and leaves of the prey in here. So there's kind of this critical range that overlaps between the owls and us. So when I started this project some years ago, I was very skeptical that owls actually were silent flyers. And so I went not far from here to Huntington to actually listen to some fly by me. And I thought, since we're coming back from lunch and trying to warm back into things, let's play a video that does some qualitative comparisons of owls. So here we go. For demonstration purposes, but the other birds have different features on their wings than owls do, and there actually have been some careful studies with actual live owls and other birds, flying them over acoustic arrays and just taking the wings themselves and putting them in wind tunnels and measuring the noise they make. So actually, it's the wings themselves that suppress the noise. So what's different about the features of, say, owls and, say, other large species raptors that may enable their silent flight. And that's kind of where the focus has been on the adaptations of the owls themselves and their feathers to reduce noise. So I showed these images here because at Lehigh we have John Audubon's Birds of America, which some of you may be familiar with. But there's also an elephant folio, which are 4 large volumes. And John Audubon, he wanted to draw all of them in life size. So this is a massive book about this big, which is sized by the turkey. It was the largest bird they had. There was kind of crinkled in there. So these are kind of here just to tie that back to the art inspiring the science. Okay, so people have been chasing these features of owl wings that supposedly make them quieter for 80 years. Okay, so Graham in 1934 identified in his short paper 3 unique features. One is this kind of downy upper surface on the top of the wing and all the feathers, and so this feels like velvet. And if you look under a microscope, these are actually carried out first over in the Batchel laboratory using Professor Goldstein's apparatus. So what we've done here is take just a microscope, and then we're looking at planes or changing the focal depth. So if you look at the no penetration surface of the vein, which is just this surface of the feather, here's the impermeable base layer. You go up a little bit higher, you see these trunks. These are called panula. And then you go up a bit higher, you see that these trunks have little branches on them, and they overlap with the ones next to them. So you effectively get is this suspended porous layer that's offset from the no penetration condition on the feather. Okay, and this pushes off the turbulence going over the wing by about 1 millimeter from the actual no through-flow condition on the surface. Okay, that's one. Now there's a leading edge comb. This is probably the most off-sided feature of the owl wings that people think they associate with the silence. This is a stiff array of fibers that go along the front. As an aerospace engineer, they look like vortex generators. One might think of it that way. And actually, the spacing of these fibers along the comb agrees with experiments for optimal drag reduction at low incidence. There have been some experiments with live owls. They take these off, and they don't fly so well anymore, and they're a bit louder. So there's a coupled aerodynamic and aeroacoustic problem with the comb. There have been some other work with serrations and things of that sort, showing that noise reductions are indeed possible. There's also some recent literature thinking, supposing that this comb has something to do with the tip vortex that's produced and the noise associated with that. So that's an ongoing area of research. And lastly is this trailing edge fringe. This will be the focus of our Wiener-Hopf approach. These are flexible filaments at the back edge of the wing, shown here with the barn owl. This is an area where you have a gradual mixing of the upper and lower flows. So instead of going from being over, say, a rigid impermeable plate to being in the pressure release region behind, you might have a gradual transition of this. Okay, so edge noise is a dominant noise source for a lot of applications, and also is a noise floor for a lot of applications. So for owls to be functionally silent, this is at least one thing they have to address, is to reduce that noise floor. So we've started out with this approach. So just for fun, we take all these things, we throw it on an aircraft, right, and it looks like this, right? So here's the future, but probably not, right? Because what we're going to do is take these features, right, so and adapt them in a useful way. We want all their benefits, we don't want any of their drawbacks. And so there's a trade-off between acoustic stealth and aerodynamic performance that's part of this problem, in my opinion. And so I'm in the right country for this. This up here is Richard Hammond on one of his programs. Okay, so the problem we're looking at now is turbulence generated by the boundary layer flowing created over the wing, and the noise that's scattered when it hits the trailing edge. Okay, so compared to conventional aircraft, what we're looking at is we're modeling the edge as being compliant and porous or poroelastic. So we've seen various combinations of these in previous talks in this program. And the research goal is to look at the acoustic power. We know that the acoustic power scales as the 5th power of velocity, which I'll talk about a little bit later. And so we want to see if it goes to be a little bit weaker, so like velocity to the 6th. That's actually by a power of Mach number. I add that exponent. So it's really, for small Mach numbers, this is getting quieter versus louder. And if you look at the data on noise produced by owls, there's this large drop that happens at 2 kilohertz. And that's where our hearing and their hearing is very sensitive. So the goal here is just to model with Wiener-Hopf the noise generated by turbulence hitting an owl-inspired edge and compare that to, say, an ordinary wing. All right, so wouldn't be complete without referencing the giants of the past and the present, I should say. So Light Hill, of course, instead of modeling turbulent flow, which is very complicated, we can represent that as a compact turbulent eddy in low Mach number flows. So we can just use it as a point source to look at our problem. Factorisation and Hall use Green's functions, actually from E&M theory was the Green's function, to show that the noise scales at the fifth power flight velocity for a rigid impermeable edge. And Crichton and Lipington extended this quite quickly afterwards to show that if you have a point reacting edge, in this case a porous edge for us, you can get a sixth power velocity dependence, so weaker by factor of the Mach number. And he, of course, employed the Wiener-Hopf technique to do this. So we're taking the physical problem on the left-hand side, quite complicated, and representing it and the modeling on the right-hand side. So we have a poroelastic, semi-infinite edge being excited by a turbulent source near the edge, and we want to find the noise in the far field. This, of course, is not what we do mathematically. We actually give it a plane wave here, find the solution very close to the edge, and apply the reciprocal theorem to get our solution. And so I want to note folks here at the program that have done extensions beyond the semi-infinite edge and have really, in getting more solutions, actually developed the theory quite well for finite porous sections and poroelastic sections. Okay, here's our plate model we use. We assume that it's small porosity. This is the open area fraction, and that all the wavelengths are large compared to the feature sizes of holes. Okay, so it allows us to kind of average over those and give it an effective porosity. So this is our plate equation, which we saw earlier on by Dr. Peter. And so if we have alpha sub h, our porosity go to 0, we just get the plate equation. And if alpha sub h here denotes this is the inertia of the flow inside the pore. And so now we have a certain section, which is the plate being forced by the pressure, and then on the other side is the inertia of the flow inside the pore there. Okay, so here are the equations we're solving. Here's our incident plane field for the reciprocal problem. Our kinematic boundary condition, so the normal flow matches the area average of the velocity of the plate and of the flow in the aperture. A porosity plate equation, here's linearized Bernoulli, which relates the pressure jump to the jump in velocity potential, and of course we have Helmholtz equation. Okay, we have the usual Sommerfeld radiation condition applied here, and this problem actually is described by two dimensionless parameters. One is the vacuum bending wave Mach number, which is related to the frequency like so, and then we have an intrinsic fluid loading parameter, which is dependent only on the fluid you have and the plate. Okay, so this is old hat by this point. We apply half-range Fourier transforms. We have a very classical kind of scattering problem. And left-hand side up to here is the usual Sommerfeld diffraction problem. And then this other bit here is due to the porosity and the elasticity. Because everything's color-coded here for if we drop everything that's colored out, then we have the classical Sommerfeld. Everything involving alpha sub h is due to porosity. And in cyan here, we see the complication is due to the elastic waves inside the plate. Okay, so and we see that here in the Wiener-Hopf equation as well as in the kernel as well. Okay, so we want to of course factorize these, and we applied the quote-unquote Wiener-Hopf magic from earlier this week, and our entire function is identically 0, and we get our solutions here. Very straightforward Wiener-Hopf, a scalar Wiener-Hopf solution. We start out numerically in terms of factorizing our kernel. So we just pull out terms such that we get j of alpha, our transform variable, going into 1 as mod alpha goes to infinity. And we just choose our path here. This is easily done. We create a code, and then we just give it an alpha, and it spits back a result for that function. Later on, we'll talk about asymptotic splitting of the kernel in special cases that gives us more insight into the physics. I haven't talked about edge conditions yet. So on a plate equation, we have a biharmonic operator, but we can only specify 2 edge conditions. Right. So if we have free edge, we have moment free and transverse shear free. And the remaining 2 conditions actually are determined as part of the solution. So if we look at our solution here as H minus, which is analytic in the lower half plane, and alpha, we have all these minus functions here except for this plus function kind of sticking out like a sore thumb, right? So this contains 2 poles in the wrong place. These have to become removable singularities, and that gives us 2 more equations to give us the 2 other unknowns, which are edge conditions, not specified. Okay, so all of this gives us phi, our velocity potential, and this is all something you would have seen in Crichton-Lepting's paper in 1970. And B here contains all this mess involving the physics of our problem. Okay, so at this point is where we say we apply the reciprocal theorem. So we want the scattered solution at some point. We just exchange subscripts, and we now have our solution due to a turbulent source close to the edge and measured far away from the edge. And our quadrupole we mentioned with Lighthill comes into play here. Now we want to look at the amplification of the presence of the edge. Okay, so we look at the ratio of the scattered field due to the field without the edge and with the edge. Okay, we'll neglect directivity for now. Actually, there are interesting things that happen with directivity as you go from velocity to the 5th to velocity to the 6th. When you add porosity, it goes from the cardioid to being a dipole progressively. But just looking at the scaling behavior, we can just look at beta as this. Okay, all we've done now is the acoustic solution. Right now I have to connect it to the fluid mechanics in some way. So now we define a characteristic velocity of the eddy, the turbulent eddy, and its length. So we get a frequency, a Mach number, and a wave number that comes out of all of that. And now we can see our acoustic power goes like, again, leveraging Lighthill's result, goes like this beta squared times velocity to the 3rd, that gives us power, times the Mach number to the 5th. So 3 plus 5 just gives us velocity to the 8th, which is the free field quadrupole we have from Lighthill. Okay, so this beta is going to knock down these powers of velocity, or as we change from rigid to porous to elastic. Okay, so we need some parameters to start to kind of look at this a bit. And actually, it was a nice set of experiments done by Michaela Herr at Braunschweig, and she looked at these elastic, flexible fibers on the edge of a rigid plate. And here's our open area porosity. Here's our non-dimensional pore size, effectively averaged over these slits, the frequency of interest, and our fluid loading parameter, which is usually very small. Okay, so our model holds in these 2 ranges were for those 2 parameters being very small, and just reminding ourselves of the variables and parameters we have there. This is probably the most important slide of the talk, so I'll take a bit of time to talk through it. Here we plot the log derivative of beta with respect to omega, our frequency, and this corresponds on the right-hand side to the acoustic power scaling with velocity. Okay, so in the rigid case, we have a frequency-independent velocity to the 5th scaling, right, as we'd expect. And here we just have the Boeing 777 just to kind of indicate that. If now we have it be rigid but porous, we have this black line. So at sufficiently high frequencies, we have velocity to the 5th, which is recovered. But as we go lower and lower frequencies, porosity actually is excellent for reducing noise. Okay, so and if we go now to elastic non-porous, we have this blue line where we have this new kind of scaling like velocity of the 7th that occurs, which is quite unexpected. Velocity of the 8th is when we have a free field quadrupole, and velocity of the 6th is when we have the scaling as if there's no edge at all. That comes from Fox-Williams. So if we have velocity of 6th and above, there's kind of no edge effect anymore. And poroelastic kind of is somewhere in the mix there. This is the scaling, and on the right-hand side is the actual noise reduction. So 2 different things. So look at this. This is relative to the rigid non-porous edge. So the porous edge gives you great noise reductions at low frequencies, as we talked about before. And as you go to high and high frequencies, it just rolls off and becomes effectively a non-porous edge. Okay, so we have these buckets that show up for the elastic plates, and the poroelastic does the best job here. All right, so, and I superpose these over with our human hearing range as well as the owl low noise range. So it doesn't quite get to velocity of the fifth, but it does give you some, velocity of the sixth, but it does give you some noise reductions on about 2 to 4 decibels. Okay, so that's the numerical results, but can we do a bit of math to get some more insight into this kernel? And so this is the, no one really needs an introduction to this, but here's the warm-up of our Sommerfeld kernel, and lo and behold, we get velocity of the fifth, right? Frequency independent here. Okay, so with the porous edge, our kernel just has now this parameter mu, which is involves our open area fraction and features involving the pore size. And this actually is a Kranz-Radlow form, which has a known result here. So this is just a correction, linear correction here, that makes no difference. And then in the other limit, where mu over k is large, you have this singular perturbation approach that Crichton-Levitin showed to be that. So now we have actually an expression showing what the key parameter is, has to be large or small to get velocity of the fifth, which is when this parameter is very small, or velocity of the sixth when this parameter is very large. Okay, now we have a physical connection between the velocity of the fifth and velocity of the sixth ranges. And lastly, for the elastic edge, this is no porosity. We can show numerically here that if we look from here to the right and from here to the left, we can establish these bounds on velocity of the seventh behavior. Okay, that depend on the loading. How about owls, right? That's how we got into this mess. Can we walk our way back out and get some information that's useful? Well, here are some chord lengths of owls. This is the number of wavelengths per chord, right? So if I draw a line somewhere along this, we have essentially non-compact silent flyers, and below we have compact flyers that are non-silent actually. So there's a misconception that all owls are quiet or silent. That's not necessarily so. And also their approach to their prey changes as well. So now we have pouncing and hawking of the smaller birds, and the larger ones go after larger prey like mice and voles. So there's a change. One part of it is that our model holds for this case, which is great because we're interested in the silent flowers. But we have this hypothesis that this going from non-compact to compact is associated with a foraging change in the owls, where silent flight is not essential. So here's a bit of a summary that we walk through. So implication for owls, this is possibly weakening the scattering effect at the trailing edge. And we had this hypothesis working that the silent flight bandwidth, the acoustical compactness, and their foraging behavior are interlinked. Implications for aircraft, they actually use these for reducing noise on slats and edges. And there have been some extensions by folks here at Cambridge on finite and more detailed edge geometries. And so just to answer quite quickly some of the questions that Anastasia had posed, where are some areas where this can go? Wiener-Hopf is very good at doing discontinuous conditions, right? But we've also been looking at continuous distributions toward the trailing edge of porosity. This goes back to the can we look at noise reductions by porosity, and can this be paired with aerodynamic implications for introducing that porosity? And we've done some work with this with Regine Hodgins in the back, and Peter Badu also in the back as well, by applying these Jacobi polynomials to solve these associated single integral equations that arise. And lastly, we have this technology we developed inspired by owls called finlets, which are streamwise oriented rails that are placed into the trailing edge. And this pre-treats the boundary layer before it scatters the turbulence at the trailing edge. And so this is essentially a two-part Wiener-Hopf problem, but now it's in 3 dimensions because you have these fins coming out of the plate. So one question would be, is there some way we could model this scattering with techniques that have been developed and talked about in the past week or 2? Okay, with that, thank you very much, and I'm happy to take questions. Yes, so in low speed, yes. So in wind turbines, the Mach number is quite low, so it's really trailing edge noise is dominating. For turbofans, where you have higher tip Mach numbers, probably not so. There may be a different range altogether.
Any other questions? If not, let's thank the speaker.